have the distinct pleasure of introducing Dr. Humberto Campins. He's the Pegasus Professor of Physics and Astronomy over at UCF. He's worked across the country and gained the position of Provost Research Professor of Physics and Astronomy and head of the Planetary and Space Science Group at UCF in 2002. He studies asteroids, comets, and other small bodies in the solar system, and tonight he's going to be talking to us about NASA's OSIRIS-REx mission, which just launched about a week and a half ago. So, without further ado, please join me in giving a warm welcome to Dr. Humberto Campins.
Thank you. It is my pleasure, privilege to be here with you tonight. And I guess this slide is pretty much, it's all been done by Janine. So I am a professor at UCF. I am the director of their Planetary Sciences Group. And I'm also a science team member on OSIRIS-REx. So I am part of the team that put together this spacecraft, and we successfully launched it last week. So we had this wonderful launch which was technically perfect and also with perfect weather. We have, thank you. Why don't we show the video then, please?
Launch. Proceeding with the count. Status check.
Go out.
Go Centaur.
Go OSIRIS-REx.
5, 4, 3, 2, 1. And liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
Speeds and pressures are so reaching pressure set plateau without range. Program is complete.
And super solid rocket booster jets.
Separation looks good. And full thrust on the arrow plan.
That is the actual
spacecraft separation.
So that's OSIRIS-REx, and it's now on its way to Bennu. Thank you. And so, as I was saying, we have team members from Japan, team members from Europe, and they were all at the launch site. We were all together, and they said, Humberto, you guys have perfect weather here. I said, not all the time. We really lucked out for this launch because the typical September weather would be either a thunderstorm, a tropical storm, or even a hurricane, right? And so it was perfect. Okay. Back up. All right. Bear with me for a second. Okay, here we go. Okay, so OSIRIS-REx is an acronym that was actually put together by the principal investigator of the mission, Dante Lauretta, and it stands for Origins. So we're going to return a sample of a pristine carbonaceous asteroid, which we believe contains a lot of information about how the solar system formed, because this type of asteroid has not been subject to any heating, so it's got a lot of that information has been preserved, and so that's where the O comes from. Spectral interpretation, we're going to bring back samples from an asteroid, so we're going to be able to validate a lot of what we've been inferring about all the asteroids from using ground-based techniques or even space-based, but all remote sensing. We have resource identification, so we're going to identify resources that can be used for space exploration, including human exploration of the solar system. Security, this Bennu is a potentially hazardous asteroid. I'll go into more detail about that later. But what that means is that it is not threatening Earth now, but its orbit could change and it could become an impact hazard with the Earth in another 160 years. So if we need to deflect this asteroid, this mission is going to help us understand a lot better how to do it. And Regolith Explorer is for the detailed study of the soil in this asteroid. Regolith is a semi-technical term for a soil. So can we go to the next slide, please? Doesn't seem to be working. Okay, so there are two main justifications for this mission. One of them is the practical one of Bennu being the most potentially hazardous asteroid, and the other one is a scientific one, which is that is going to tell us a lot about the origin of the solar system, and specifically about the type of molecules that existed on Earth before life formed. So the sample that we're going to bring back from Bennu is likely to tell us a lot about how life formed on Earth and how it may have formed elsewhere. And it is also going to be enabling human exploration to asteroids and to Mars. And it's also going to be enabling us to develop the mining of asteroids, again, for space exploration, and even to bring some of those materials back to Earth. So there are a number of justifications. The two main ones were the ones that I mentioned. The practical one of deflecting an asteroid that could be threatening us, and the scientific one of the origin of these molecules that might have... See, I may not be pointing this where I need to. Could we have the next slide? Okay, thanks. Okay, so about the threat of asteroids impacting Earth. As individuals, you do not need to lose any sleep over this, because the chances of this happening during our lifetimes are minimal. So you do not count on winning the lottery to pay your next month's rent or mortgage. Therefore, you should also not worry about an asteroid hitting us during your lifetimes. However, large impacts have occurred, and unless civilization does something to prevent the next large impact, we will not continue to exist on Earth. An impact large enough to wipe out civilization will happen unless we prevent it. So I just wanted to clarify that as a civilization, this is a very important endeavor. But as individuals, don't worry about it. Oops. There we go. Okay, so OSIRIS-REx is only the fourth NASA mission to bring back a sample. The Apollo missions brought back lunar samples. Then the Genesis mission brought back samples of the solar wind, which tells us a lot about the composition and the isotopic, specifically the isotopic composition of the elements in the sun. Stardust brought us back dust from the tail of a comet, and that has told us a lot about how comets formed and how the solar system was mixed. And then OSIRIS-REx is going to bring back a sample of a primitive asteroid. If we look at the sample return missions from other space agencies, we have Apollo, the Soviet Luna brought back samples from the moon also, then Genesis for solar wind, comet tail from stardust, and then JAXA, the Japanese space agency, brought back a sample from asteroid Itokawa, micrograms, but even with those micrograms, the Japanese scientists have done wonders in terms of extracting very important information about that type of asteroid. And now JAXA has already launched Hayabusa 2, that is on its way to another primitive asteroid, and they will get there about 6 months before OSIRIS-REx gets to Bennu. So some of their experience approaching that asteroid will be useful to us. And then, of course, we launched and we're on our way to Bennu. Okay, now NASA is most famous for the human space exploration, but robotic exploration is very important, because if you don't have humans on your spacecraft, you can take they're much cheaper. They can be smaller because you don't need all the life support, and you can take higher risks. So you can do things that you do not need humans to do, and you can then prepare for humans to come. So there are a number of very important roles that robotic explorations will serve. And here are some examples of communications and weather satellites, of the rovers on Mars, of Cassini in Saturn, and of the New Horizons in Pluto. Now, why sample return? If we have meteorites, most of which come from asteroids, why do we have to go to an asteroid to bring up a sample? And there have been 2 cases of meteorites that where we have observed the object enter the atmosphere and then recover the meteorites. And in both of those cases that we know enough about the process, we've determined that 99.9% of the mass that enters the atmosphere is lost. So what we recover when we find a meteorite, what we recover is 0.1% of what entered the atmosphere. So we don't know what that 99.9% is. Chances are that what we do recover, it is the most compact and the material that is most likely to survive atmospheric entry. So bringing back samples will tell us what that 99.9% is. And chances are that the most interesting stuff is in there. And also, if we bring back samples, future scientists will invent new instruments and new techniques with which we can analyze it. Putting, state-of-the-art analytical equipment into spacecraft is just not practical. But in addition to that, there are analytical techniques that haven't been invented yet that could be used on future samples, like we are now still using on lunar samples and on meteorites. So there's a very, very strong drive for all of the space agencies, including the European Space Agencies and the Japanese Space Agency, to bring back samples from asteroids and eventually from Mars. Now, what about, what is it that Bennu will tell us about the Earth? It turns out that the Earth and the Moon went through a phase when the surface of both of them was molten rock. So there was not a solid surface, but a magma oceans. And if they had any organic molecules that they formed with, they were all burnt during that phase. And when a solid crust forms, that crust has been exposed to such high temperatures that it is inert. It has been basically sterilized. And it is impacts with comets and asteroids that brought Earth the organic molecules that were there before life formed. However, determining what those organic molecules were by studying material on Earth is essentially impossible because it's been transformed so much by all of the geologic processes. So by studying what we bring back from Bennu, we will understand the inventory of organic molecules that existed before life formed on Earth, and that will help us understand how life formed and evolved on Earth and how it may have formed elsewhere. So this is a very important step. Okay, so this is a quick summary of all the asteroids that have been visited by spacecraft. And it is a surprisingly large list. It's wonderful. So the largest asteroid is Ceres here. It's about 1,000 kilometers across. It's about the size of Texas. And Bruce Willis has not been to it yet. And here's Vesta, which was visited by the Dawn spacecraft. By the way, Dawn has visited first Vesta and then Ceres. And actually before that, the Rosetta European Space Agency spacecraft visited 21 Lutetia. And notice, this is Ceres, Vesta, and they're getting smaller and smaller. And then if you take the smallest group here, it's expanded here, Ida, Gaspra, this is Ida, Eros, Gaspra, I can't read the other names. And then out here somewhere is Bennu. And so here we have OSIRIS-REx that is going to be going to Bennu, which is one of the smaller of these asteroids. It's about 5 blocks across, and it has this shape, and I'll give you some more details on it. Now, this is Itokawa, the asteroid from which the Japanese Space Agency brought back a sample. And asteroids are rubble piles. So these guys have been subject to so many collisions that they're essentially a gravitationally bound rocks of different sizes that are the result of a collisional evolution. And so Bennu is the name of the asteroid that we're going to, and the name got chosen by an international contest that was run by the Planetary Society, and the winning entry came from a then 9-year-old boy from North Carolina, Mike Puccio, and he chose this name, which is a mythical bird that came from the heart of the god Osiris in the Egyptian mythology. So they chose a name that was appropriate to the name of the spacecraft that was headed over there. We know considerable amount about Bennu, and we chose that as our target in part because we knew so much about it. It came relatively close to the Earth in, my apologies. It came relatively close to the Earth and at this time, and we were able to observe it with their radar, both in Arecibo, in Puerto Rico, and in California, and we determined its shapes. We've also were able to take some spectra, and we have a rough idea of what its surface characteristics are, but we know almost nothing about the details of the surface. So, for example, now that the spacecraft has launched, we're going to be starting to test the instruments, make sure that they all are functioning correctly after launch, and we're going to be practicing all of the data gathering that we're going to be doing in 2 years when we get to the asteroid with synthetic models of the asteroid. And we're going to, for example, in my case, since I work on the imaging team of OSIRIS-REx, we're going to be testing all of our software for producing maps of the surface on a case where the surface is very rocky, and the other extreme where the surface is very dusty, and somewhere in between. So by the time we get to Bennu, we will the acquisition and analysis of the images will be second nature to us, so we can be ready to interpret whatever terrain we find there. And then, based on those maps, choose a site for the spacecraft to then do the touch and go maneuver and bring back the sample to Earth. So this is the mission timeline. We launched successfully, and then we're going to be we're going to actually come by the Earth in September of next year, and we will use the Earth's gravity assist to change our orbit slightly so that we encounter Bennu in August of 2018. 2019 and 2020 will be my busiest, probably the busiest years of my career. The project office actually wants me to move to Tucson during that time. They said, "Don't worry, we'll buy your time out of the University of Central Florida. You can move here." And then we will be operating the spacecraft, making decisions basically day to day, depending on what the images tell us. And then the sampling is done in 2020. Maybe early 2021, and then we head back to Earth in 2021. We get back in 2023, and then there will be the sample analysis that is part of our mission, and then the samples will be available to the community as a whole for years to come. And this is a little cartoon of the touch and go maneuver. So the spacecraft will deploy its mechanical arm with the sampling mechanism at the end. And so we will approach the surface of the asteroid at minimal horizontal and vertical velocity, so that when we touch that surface for 5 seconds, there's a spring on that mechanical arm that will absorb some of the energy when we touch the asteroid, and then push the spacecraft away from the asteroid without having to fire the thrusters. We don't want to fire the thrusters near the surface of the asteroid. We don't want to kick up the dust that could blind our cameras. So, and that's the end. So if you want to keep in touch with us, here are all the ways you can find us on the web, and I'm open to questions.
Get the microphone so that everybody can hear your question. I see this one first. Everyone else, Dr. Humberto, you can point to the person and I'll run the mic.
Thank you, Doctor, for explaining all that to us. Question about your findings. If you do not find any organic life forms or primitive organic life forms.
No, not life forms, molecules.
Oh, I'm sorry, molecules.
There's
I'm
a
sorry.
big difference
Yeah,
between
huge
molecules
difference.
and life.
Huge difference. Huge difference.
And we still don't know how that transition happened. That's
Yeah.
why we're interested.
If you do find them, wouldn't it be dangerous to bring those things into our atmosphere, onto our planet?
Well, we have a very strict contamination protocol, so we don't contaminate the sample, and that the sample does not get exposed to anything except very clean, contained rooms. So there isn't danger. Besides, we get tons of that type of material into our atmosphere every day. We just are not able to analyze it because most of it gets burnt in the atmosphere, or it falls into particles that are so small that it's impossible to capture them and analyze them. So we're not bringing in anything that is not already here, but we're bringing it in a pristine enough environment that we know that there will not be any terrestrial contamination of the sample, so that everything that is in there belongs to the asteroid. And so we have a number of other techniques to ensure that. But yeah, we're not bringing anything. I think there was another question here. Janine, could you also help me keep track of who's raising their hand? Thanks.
Hi, thank you for coming tonight. I wanted to ask if there was any chance to retrieve any water ice from the asteroid, and if not, are we going to try to get a sample of, water ice that's not of our planet, of course, to just kind of get an idea of what existed before it impacted us and turned into, the water that we drink and use daily?
Very good question. So we know that at least part of the water that the Earth has was brought here by impacts with asteroids and comets. And in the case of this asteroid, we do not anticipate finding water ice on its surface because its orbit keeps it relatively close to the sun. It's very similar to Earth's orbit, and its surface temperature is high enough that we don't expect any water ice. However, if there is water ice, we will likely want to sample that site if we detect any water ice. We have the camera with the number of filters, and we have 2 spectrometers on board that will tell us the composition of the surface. And most of us on the team, if there's an area that is rich in water ice, it has probably been subject to the lowest possible temperature, so we want to sample that area. Although there is at least one member of the science team that says, no, stay away from the water. It can cause trouble, because if we put the water in the capsule on the trip back, it could react with some of the minerals that are there, and then we wouldn't know what was there before. And so there are a number of arguments in favor and against, but we don't think we're going to find water ice here. However, water ice has been detected on on the surfaces of at least 2 asteroids from the ground, and hydrated minerals. So the result of water ice melting and reacting with these silicates that are in these rocks have been characterized in a number of meteorites. So we know that some of the asteroids contain hydrated minerals. Some of them have water ice on their surfaces. That strengthens suggestions that have been made for many years that the Earth formed dry, and it was ice from further away from the sun in the form of asteroids and comets that brought at least some of the water that we have.
The guy, she's been holding her hand up the longest.
All right.
I'm coming. Oh, but it's more fun. Actually, there's people in another room, so we have to make sure they can hear.
So in that 5-second scoop, which is crazy, how much are you anticipating getting? Like what's the mass, the amount, the stuff that you're going to bring back?
I'm going to try to bring up another slide that I had of the actual mechanism, but that's a very good question. The minimum that we expect is 60 grams, and the maximum is about, so 60 grams is about, how many is that in ounces? 2. Okay, thank you. I'm used to metric. And then the maximum is going to be about 2.5 kilograms, so I would say about 5 pounds, 6 pounds. And what's interesting about this type of asteroid is that it's been subject to so little processing, so little heating, that every grain in there is likely to tell us a different story because they have not reacted with the other grains around them. They've been exposed to different conditions. So we can have a number of processes that are recorded there. We know from primitive meteorites that some of them have pre-solar grains. These were grains that formed around stars before the sun and then ended up in the solar nebula and survived the whole process of formation of the asteroid and then the process of an impact on that asteroid bringing a little piece to Earth. And then we eventually in the laboratory found out that the isotopic composition of that microscopic grain was unlike anything else in our solar system. So we've actually been able to determine that there were at least 16 different stars that contributed to the formation of the solar system. Janine, will you help me with who was next?
I think it was him.
Thank you. You talked about you were uncertain of the surface of the asteroid. What are you using to collect the sample? If you have a scoop, is it a little drill? I mean, what if you land on something that's a solid rock surface and you're trying to scoop it? I don't understand.
Yeah,
there you go.
by the way,
This
is the mechanism.
Thank you.
And it is not crazy. We have, it might have been crazy about 8 years ago, but now we have tested this at 0G. We have tested it under a number of conditions. And so what this is the head of that mechanical arm. And so once we touch the surface, these nitrogen bottles will fire and will push the flow of the gas into the surface, and that will fluidize any dust that is in there and eventually go into our containers here. Then the outside of the mechanism has these surfaces that are like a glorified Brillo pad, so that if there's any dust, it'll fall into it and it will not come out, and those will be brought back. Pebbles can also fall into some of the outside of the mechanism, so we have different ways of bringing back the sample. But we will spend about 1.5 years mapping this asteroid in detail, so that we will pick at least one site. We'll have one main site and 2 backup sites that will contain dust. And we have many reasons to expect dusty surfaces on asteroids. Itokawa is an example. It had some areas that were where fine dust was pooling. And in the case of Bennu, we have other reasons to suspect that there's going to be at least as much dust as there was in Itokawa. But part of my job on this team is to create these maps and identify the areas that will be rich in loose dust so that we can sample those. And it turns out that it's very difficult to get away from dust because fine dust will adhere to almost anything. So chances of us hitting a rock that is completely devoid of dust are essentially zero. Go
Doctor,
ahead.
thank you for the explanation. You had mentioned that Bennu poses a risk of impact, I think you said 160 or some odd years from now.
That's right.
I'm curious to know what the mass of Bennu and the probability of impact is as compared to the infamous Apophis asteroid that is potentially a threat, I think, in the 2030s. But I know it's a very slim risk.
That's right. Apophis is actually lower than Bennu, but Bennu is not threatening Earth now. Neither is Apophis, right? But in the case of Bennu, it is got about one chance in 2,500 or 3,000 approximately, and the chances of that happening depends on something called the Yarkovsky effect, which is a way in which these guys heat up and cool down and in which direction is the afternoon side. And so all of that we're going to measure. So in case we have to deflect this one, which I don't think we will, but in case we have to deflect this one or another asteroid, we will know a lot more on how to do that. The mass depends on the density. We don't know the density of Bennu. We estimate it to be approximately 1, so it's the same density as water. We will know a lot more after we get there and we study it. Now, this thing is, the Bennu and most near-Earth asteroids are rubble piles. So we cannot go and attach a rocket and push them away because they will just disperse them. We need to be very careful. We understand the distribution of the mass and how to gently nudge it away so that we don't end up with a shower instead of a single impact.
Question, how different do you think that the material is going to be from that was already collected from Itakawa? And this origin material, are you expecting it to have like a different crystal lattice? Is it something that you have never seen before? What are you expecting?
We're
out of it?
hoping
And
it's nothing we've ever seen before.
Right, and
right?
what kind of...
And we have a rough idea, and the rough idea comes from the different meteorites, right? Itokawa is the most common type of meteorite. Is the composition of that asteroid is basically it's the same composition as the most common types of meteorites, the ordinary chondrites. But it was very important to make those measurements and determine, for example, the effect of space weathering on the surface of the asteroid that makes them look different from the meteorites that we have on Earth, and some of those things. In the case of Bennu, the spectroscopic measurements we made from the ground suggest that it's more like a carbonaceous chondrite, which is a meteorite that contains more volatiles, contains water, some hydrated minerals. And again, it is that 99.9% that doesn't make it through the atmosphere that we would like to know what it is. Is it finer material? Is it more organic material? What is it? The crystalline structure will vary. Some of the material will have a very strong crystalline structure. Some of the material may be amorphous. Some of the material will be hydrated. Some will be anhydrous. And then on top of that, we have the elemental composition and the isotopic composition. All of that is going to be telling us part of this whole story of how the solar system formed. And so I am sure that nature has surprises for us in this asteroid.
Very nice, thank you.
So we have time for one more ask everybody question, but if you have questions afterwards, Dr. Campins will be able to stick around. Do you want to pick the last one to talk to everybody, Dr. Campins? I picked the last couple, so it's your turn.
Do I have to choose? Boy,
yeah, it's your turn. I picked all the other ones.
Okay, I don't know. Somebody use the honor system and tell me who was the one who had the
That.
Okay.
Oh, this one? What do you, okay. Don't worry if you didn't get to ask your question.
If
You
not,
can go down
please
and ask
come and
it.
ask the questions down here.
He's been waiting.
That's okay. Thank you. It's more of a technical question as opposed to.
Could you
your
speak
collection.
up?
More of a technical question as opposed to your collections. About your mapping process. Are you using like a LiDAR system for that?
There's a LiDAR. There's actually 2 LiDAR systems on board. One of them, which was provided by the Canadian Space Agency. So thanks to our neighbors in Canada, we will not build a wall with Canada. And oh, I'm sorry, this is space science, not political science. But no, I am actually delighted with this because we have a very strong international team. The Canadian Space Agency, the Japanese Space Agency, the European Space Agency, and in the case of the European Space Agency, 2 of our co-investigators are in the Nice Observatory, which is in the south of France. So every summer, I have to go work in the south of France. Shucks, somebody's got to do it. But anyway, back to your question. Now I forgot.
Well, it was really a 2-part question. I was curious if you're using a LiDAR system, and then the second part of that, if you are, what kind of information are you getting about the surface?
So the LiDAR is used for generating a detailed map of the topography of the asteroid and of the distance between the spacecraft and the asteroid. And then we will use that to create this digital shape model of the asteroid, and then the maps that I will be in charge of, or partially in charge of producing, will be projected onto that digital shape model. And there will be an actual interaction between the LiDAR team and the imaging team on refining the shape depending on how well our maps are projecting onto their shape. So there's a little bit of iteration between the two. And then we have to stitch the images together, produce the mosaics, and project them onto that digital shape model, and in order to make sure that everything that we're seeing is exactly what the spacecraft will encounter once it gets closer to the surface. Does that answer the question?
All right, everybody, please join me in thanking Dr. Campins for his wonderful presentation today.